Okay, now what we're going to do in this section, section 4.3 on right triangle trigonometry, is we're going to define the 6 trig functions, not based on the unit circle, but based on a right triangle. Now, we remember from our geometry days, and hopefully we remember from our geometry days, that a right triangle is, of course, a triangle that has a right angle. Therefore, it's going to have 2 acute angles. If I call this angle here theta, then the leg, remember these are the legs, that's the hypotenuse, then the legs, this leg is next to theta, so we call that the adjacent leg, or we just abbreviated ADJ. This leg over here is opposite the angle, the opposite leg, or OPP, and of course the longest side is always the hypotenuse, HYP. And we're going to define our 6 trig functions based on this right triangle. And here's the definitions. For the sine of theta, the sine of this angle is equal to the opposite leg length compared to the length of the hypotenuse, this fraction. And that the cosine is the adjacent leg compared to the hypotenuse, the adjacent to the hypotenuse. The tangent of theta is the opposite leg over the adjacent leg. Now when I say the legs, I mean their lengths. Okay, the length of the opposite side or leg over the length of the adjacent leg. And then you can see these 3, of course, are the reciprocal of these 3, just like we defined them when we were using the unit circle. Now if you're saying, oh, wait a minute, how do we have this luxury? How do we know that the values are going to be the same? Well, if you look at my diagram, and it's not a great diagram, but I've tried to draw a unit circle, and I have an angle theta, and I drop down the perpendicular here from point P, which is the point XY. And of course that means if this is the point XY, X to the right, Y up, and the hypotenuse is 1. I extended this little bitty right triangle to include a bigger right triangle in such a way that I know that these 2 triangles are similar because they both have the right angle, they both have the same acute angle here, theta, angle, they are similar triangles. And you may remember with similar triangles, CSSTP, corresponding sides of similar triangles are proportional. So we can set up the proportion. Look what I've done. I've set up 6 different proportions here from the little guy to the bigger guy. Okay? For example, X is to Y. This side is to this side as the adjacent side here in red is to the opposite side here. Notice, adjacent to opposite. And I looked at as many different ways that I could compare 2 sides here, and I have them listed here, although it's kind of leaning a little bit to the right here. X over Y, Y over X, X over 1, 1 over X, Y over 1, 1 over Y. Now, if we look at the definition here using the unit circle, we know that the cosine of theta is X, or X over 1. The sine of theta is Y, or Y over 1. The tangent of theta is Y over X, and then we have these blue definitions here for the unit circle that we had in the last section. Well, using these, I can come right over here. Look, X over 1. X over 1, that's adjacent over hypotenuse. Adjacent over hypotenuse, that's the cosine of theta. That's how we defined it right here, the adjacent over the hypotenuse. Because the sides of the 2 triangles are proportional, we can make this definition hold. And we can use a right triangle to define our trig functions. And I've got them here lined up, cosine, sine, tangent, cotangent, cosecant, and secant. And they match up, the ones from the unit circle match up to the ones on this right triangle definition because of the similarity of the 2 triangles and because CSSTP, good old Mr. Haydn, corresponding sides of similar triangles are proportional. Alright, so now we have an alternate way to find trig functions. Now notice, this is only for acute angles because we're only looking at one of the acute angles here in the triangle. So we're going to have to make some adjustments if we want to look at an obtuse angle, or if we want to look at a right angle, or if we want to look at something even bigger, and of course negative angles and such. But first things first, we'll work with some acute angles. Look over here, I have some examples, and I drew some diagrams here to help me. I have found that when I'm doing these problems, and I'm going over this with a student that hasn't really had a lot of this, it helps to have the diagram so that you can kind of, point stuff out and you can kind of keep track of it visually rather than trying to keep track of it all in your head. Suppose that a right triangle, triangle ABC, has legs of lengths 6 centimeters and 3 centimeters. Now those are the lengths of the legs. Evaluate the 6 trig functions for angle B, where angle B is the larger acute angle. So I have this triangle drawn here. I have angle B right here. And the legs are 6 centimeters and 3 centimeters. So this would be the larger side. This would be the smaller side as far as the legs are concerned, because this is the bigger acute angle. At least it looks like that in my diagram. So now I can use, and of course it's not necessarily drawn perfectly to scale, but now I can use the Pythagorean Theorem and I can find the length of the hypotenuse. You remember a squared plus b squared equals c squared. Right? Well, this is my hypotenuse, that's my c. This might be my a and my b, so I have 3 squared plus 6 squared equals c squared. 9 and 36, 45 equals c squared. C is equal to the square root of 45, not the negative, the square root of 45. And of course, this means if I simplify the radical, because 9 divides into that, 3 square roots of 5. So there's my hypotenuse, and this would also be in centimeters. Now when we find the trig ratios for all 6 of these, our answers are not going to be in terms of centimeters, because we're going to be looking at ratios of these measures, and of course the centimeters would cancel out, so we're just looking at a value, a number, a real number. So let's go the sine of theta, of angle B. Now you can write angle B like this. Sometimes they'll just go ahead in textbooks and they'll just write it like that. I kind of like this a little bit better. Well, that's just my own personal preference. I can live with that. Now the sine of angle B, according to this, is the length of the opposite leg over the length of the hypotenuse. So the length, with respect to angle B, this would be the opposite here. This would be the adjacent, and this of course is the hypotenuse. So it would be 6 over 3 square roots of 5. 6 over 3 square roots of 5. Now we're not going to leave it in that form, because we don't want to leave the radical in the denominator. I'll multiply top and bottom by the square root of 5, but before I do, I'll cancel a 3 there and a 3 there, and it leaves a 2. Type top and bottom by the square root of 5 gives me 2 square roots of 5 over 5. And there's my first one. Now I'm also going to do the cosine of angle B, and that is going to be 3, the adjacent, over the hypotenuse, 3 over 3 square roots of 5. I can simplify a little bit, so I have 1 over the square root of 5, multiply top and bottom by the square root of 5, and I have the square root of 5 all over 5. The tangent is the opposite over the adjacent. The tangent of angle B would be the opposite. With respect to angle B, the opposite is 6 over the adjacent is 3. Oh, that one's really nice. 6 over 3 is 2. By the way, just kind of looking there, notice how the sine and the cosine, the side that's in the numerator is one of the legs. In the denominator, it's the hypotenuse, the longest of the 3 sides. Well, that means this number here is always going to be between 0 and 1. As long as we're looking at acute angles here, this is going to be between 0 and 1. It's never going to be bigger than 1. Okay, and we only get to 1, as it turns out, for a 90-degree angle. You may remember that from the table I told you to memorize a while back. I hope. So now, let's go ahead and do the last 3. We'll do the reciprocals. The cosecant of angle B is the reciprocal here of this. Now, I've already kind of got it right here before I started simplifying, and I had 6 over 3 square roots of 5. I'm going to write that as 3 square roots of 5 all over 6. 3 square roots of 5, the hypotenuse, all over the opposite 6. Now I can go ahead, of course, and simplify, and I have the square root of 5 over 2. The secant of angle B is the reciprocal here. Now remember this guy, before I started simplifying him? In fact, look at this guy, even before I started simplifying it further. I had 1 over the square root of 5, so that would be the square root of 5 over 1, which is the square root of 5. The cotangent of angle B would be the reciprocal of 2, which is, of course, 1/2. And I have the 6 trig functions based on that triangle. I draw the triangle out, I find any missing sides using the Pythagorean Theorem, because it's a right triangle, and then I use these ratios, which I need to memorize. Suppose that the sine of theta is 3/4 for an acute angle theta. Evaluate the secant of theta. Now let's go over here. I've drawn this triangle in such a way, right triangle, that I put theta right there. If I know that the sine of theta is 3/4. That means that the ratio of the opposite leg to the hypotenuse is 3 to 4. Now that doesn't mean that this side is 3 and this side is 4. This side could be 6 and this could be 8, or this could be 9 and this could be 12. But it's in that ratio of 3 to 4. It would simplify to 3 to 4. It might have a common factor. So, if you'd like, you can write 3 and 4, which is what I prefer to do, or you can write 3x and 4x, so you have that extra factor. I used the Pythagorean Theorem here to find this guy. This time I'm finding a leg. Leg squared plus 3 squared equals 4 squared. So I would have a squared plus 3 squared equals 4 squared. So that's a squared plus 9 equals 16. A squared equals 7. A is the square root of 7. So then this guy would be the square root of 7, or the square root of 7 times x, if you want to have that extra factor in there, because of, don't put it on the radical. Here, we'll put it out in front. And you can look at that in that form. I don't think you need to put the x's if you just recognize the fact that it could be a multiple of these, but that's okay. If you want to put the x's in, that's fine. I want the secant. That's the the opposite over the hypotenuse. That is wrong. Oh my goodness, I got all the way through here and I just discovered I had this one upside down. Holy smokes, it's a good thing I did the secant example over here. Go back and change your notes, people. This is the hypotenuse over the adjacent. I wrote it down wrong. Did I write it down wrong over here? I hope not. No, here I got it right, but here I didn't. Okay, so now, thank heavens, we found that mistake, so we don't confuse you any more than I already have. And I'm going to find the secant of theta over here. It is the hypotenuse over the adjacent. It is 4 over the square root of 7. The secant of theta is 4 over the square root of 7. 4 over the square root of 7, hypotenuse over adjacent. Now I'll multiply top and bottom by the square root of 7, and I get 4 square roots of 7 all over 7. And that would be the secant of that angle. And I didn't need all 6 of them, I just wanted to find one specific. Now, we've already done a little bit of stuff with 45 degrees and multiples of 45 and 30 degrees and multiples of 30. Although we were doing mostly in terms of radians, we were using pi over 4 and pi over 6 respectively. But I'm going to go ahead and use these right triangles that I've drawn out here to find the values in question. Now remember, if this is a 45, 45, 90, there's a relationship in the sides. And that means that these two guys are the same length. I'll just call it x. And this side here is the square root of 2 times the length of either one of the legs, because the legs are the same. So this is, I'll try to write it here on an angle, 2 over the square root of x. Excuse me, 2 times the square, let's try that again. X times the square root of 2. I think secant still bothers me. I'm scrambling in my thoughts here. So this is x times the square root of 2. So let's find the cosecant of 45 degrees. Now the cosecant is right here. It's the hypotenuse over the opposite. It is the hypotenuse over the opposite. So it is x square root of 2 all over x. That's the square root of 2. Let's find the secant of 45 degrees. And now we have secant right. We can refer to here. Hypotenuse over adjacent. Here's our angle. Hypotenuse over adjacent. It's the same ratio. Kind of makes sense because the two legs are the same length. I get the square root of 2 again. And then the cotangent of 45 degrees would be the adjacent over the opposite. It would be the adjacent over the opposite. It would be x over x, or just 1. Now we can find their reciprocals. We could find the sine, the cosine, and the tangent by taking the reciprocals of these amounts. Okay, one more chance here with the 30, 60, 90 right triangle. So let's see if I mess this one up like I just did, calling it a 30, 60, 90 right triangle. What else is it going to be if it's got a 90? This guy here is 30, this guy here is 60, this guy here is 90. Again, a relationship in the sides. I like to use the short leg as my initial measure. I'll call that x. The hypotenuse is twice as long. Call it 2x. And the length of the longer leg would be this distance times the square root of 3, or x square roots of 3. Now I'm going to find the sine of 30 degrees, which you should already have memorized. I'm going to have the cosine of 30 degrees, and I'll finish with a flurry with the tangent of 30 degrees? Well, again, sine is opposite over hypotenuse. Opposite over hypotenuse. This is going to be x all over 2x, which simplifies down to a half. The sine of 30 degrees is a half. Whether you're using a unit circle, like we did before, or you're using the right triangle. The cosine of 30 degrees is the adjacent over the hypotenuse, so that's x square roots of 3 all over 2x. I can cancel an x, and I get the square root of 3 over 2, which should be what you remember it to be. I hope at least. This next part here, the tangent of 30 degrees, the tangent, remember, is the opposite over the adjacent, so it's the opposite over the adjacent. It is going to be x all over x square roots of 3. Now I can cancel an x top and bottom, and I get 1 over the square root of 3, but I'm going to have to rationalize my denominator, multiply top and bottom by the square root of 3, and I get the square root of 3 all over 3. And we have found those. So there's a lot of good information in here, and we're going to expand on this in the next video, but you need to take the time to try to memorize this. Now there is a way that some students use for remembering at least these three, and because you know these three, you can know these three because they're just the reciprocals, and that is Sohcahtoa. Sohcahtoa. Sohcahtoa, sine, see the S here, is the opposite over the hypotenuse. Cosine, the C, is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. And students kind of remember it that way. Now, I was never taught Sohcahtoa when I was in school, and when I started teaching pre-calculus many years ago at good old El Dorado, I was teaching a class and I gave them a test on trigonometry, right triangle trigonometry, and I noticed even though the kids weren't sitting next to one another, on several of the papers I saw this written down. And I thought, well, wait a minute, they must be cheating. They've got the same thing on their paper and it doesn't make any sense. And I couldn't figure out what they were trying to do here. And I asked them when I passed back their papers, I said, it's a good thing you guys that had this written down weren't sitting right next to one another. I would have thought you were copying. And they said, no, one of my teachers the year before, I think it was good old Mr. Hanlon, had taught us about Sohcahtoa, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And there's different ways you can remember the letter in the order, but you just practice writing it down a couple, 3 times, and you'll have it for the rest of your life.